Machine learning is universally defined as a subset of artificial intelligence where computers learn from data to recognize patterns and improve performance without explicit programming. This concept was originally articulated by Arthur Samuel in 1959. The consensus is that machine learning serves as the primary engine for modern artificial intelligence advancements. It powers critical applications ranging from autonomous vehicles and medical diagnostics to fraud detection and personalized content. However, for the senior engineer or tech lead, the definition is less about what it is and more about what it requires to sustain. The field is broadly categorized into supervised, unsupervised, and reinforcement learning. Each utilizes different data structures and feedback mechanisms. While deep learning is distinguished as a specialized branch requiring vast computational resources, traditional machine learning remains effective with smaller datasets. The real challenge lies in the lifecycle. It is shifting software development from rule-based programming to data-driven pattern recognition. This enables systems to improve performance autonomously without explicit reprogramming. Here is the thing that separates machine learning from traditional software development. In traditional programming, if you write code, you know exactly what it does. If the input is A, the output is B. It is deterministic. Machine learning is probabilistic. When a machine learning model processes an input, it does not give a single answer. It gives a probability. It might say there is a 95% chance this is a fraud transaction. This fundamental difference changes everything about how you build, test, and maintain the system. You cannot rely on unit tests in the same way. You cannot simply check if the code compiles. You must check if the model performs within acceptable statistical bounds. Now consider the data. In traditional software, data is an input. In machine learning, data is the product. The success of a project is heavily dependent on the quality and curation of training data rather than just algorithm selection. This is a critical gap between theoretical understanding and practical application. You need structured, project-based learning roadmaps that bridge foundational math concepts with hands-on implementation. But for the operational side, you need to treat data with the same rigor as code. You need to version your datasets. You need to track where the data came from. If you change the data pipeline, the model behavior changes. This is known as data drift. If you do not track this, you cannot reproduce your results. You cannot debug a model if you do not know which version of the data trained it. This brings us to the experimentation phase. This is where the engineer spends the most time. You are testing hypotheses. You are tuning hyperparameters. This is an iterative loop. You train, you evaluate, you adjust. The challenge here is that the environment is noisy. A small change in the data might result in a massive change in performance. This is why you need validation sets that are separate from your training data. You need cross-validation to ensure the model is not just memorizing the examples. You are looking for generalization. You want the model to work on new, unseen data. This requires a shift in mindset. You are not looking for bugs in the code. You are looking for overfitting in the model. Once you have a model that performs well, you move to deployment. This is where traditional continuous integration and continuous deployment fall short. You need a model registry. You need to store the model artifacts alongside the code. You need to know which model corresponds to which production environment. This is not just about storing a file, it is about lineage. You need to know which feature engineering steps were applied. You need to know which version of the library was used. This is essential for reproducibility. If the model starts failing in production, you need to be able to roll back to a previous version that worked. You need to be able to compare the two versions to understand what changed. After deployment, the work is not done. In fact, that is when the real work begins. Models degrade over time. This is called concept drift. The world changes. The data distribution changes. A model trained on data from last year might not work on data from today. For example, a fraud detection model might stop catching new types of fraud because the criminals are changing their tactics. You need continuous monitoring. You need to watch the performance metrics in real time. You need to set up alerts when performance drops below a threshold. This is not just about system health. It is about model health. You need a feedback loop. You need a feedback loop. You need to capture the predictions and the actual outcomes to retrain the model. This creates a continuous improvement cycle. There is also a critical gap regarding ethical oversight. Experts emphasize that while technical expertise is not required for all, leaders must understand machine learning risks, including algorithmic bias and privacy concerns. This is to ensure collective societal benefit. You need to audit your models for fairness. You need to ensure that the model is not discriminating against certain groups. This is not just a moral obligation, it is a legal and reputational risk. You need to document the limitations of the model. You need to be transparent about how the model makes decisions. This is becoming central to deployment strategies. Automated machine learning tools are democratizing access, but they do not remove the need for governance. The trajectory is clear. Machine learning is evolving from a technical novelty into a foundational infrastructure for future innovation. It necessitates a balanced approach between technological capability and responsible governance. For senior engineers, the path forward involves operationalizing machine learning models effectively. This means building pipelines that handle data, models, and metrics together. It means accepting that the model is a living system that requires care. It means understanding that the code is only one part of the equation. The data is the other part. The monitoring is the third. The monitoring is the third. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.